All right, so what are we looking at here? So I've done all the ACT, must be on to that, yes. So your lesson didn't actually today really talk about solving exponential equations. It's just here for review, as it was a previous lesson. All right, so I'm going to write down what is very important. It's called log is bay. A logarithm base b with an argument equal to something, which I just called letter E, is equivalent to a base with an exponent equal to an answer. Now, there is an understood 1 here. This has a 4. I need to divide my 4 out. If you want decimals, so be it. I'm just going to leave it as it is. It's going to be 17 over 4. My base is the letter E because bases have exponents. My exponent is negative 2x. And my answer is 17 quarters. So I'm going here. That's where I'm going with this. The base again was E, log base E. The answer was 17 over 4, and it has to equal negative 2x. And I'm just going to divide by a negative 2 on both sides. Log base E is that natural log. Remember this idea? Log base E is the natural log of 17 over 4, and then divided by negative 2. And this is the answer. I mean, you can stop here if you want, or you can push some buttons. There's a natural log of 17 quarters. She is divided by negative 2. Ta-da! Negative 0.7235. It's up to you. Write it if you want. I don't really care. Next one on here that I've got bolded and highlighted is number 5. And sorry, I took away the whole log is base thing there. But think about that. We have base. Now, this has the same problem that one did. There's a lot of little baby steps you got to do. Like you got to subtract 1 and get 5. And then you have this 1/3. So you just multiply both sides by 3. What's the cancellation? Now you have a base, you have an exponent, and you have a result or an answer. So you have a log whose base is 10, which is understood. The argument is 15, and it has to equal negative 4x. Log is bay, children. Log is bay. I'm going to divide out the negative 4, and if I don't have a calculator at home, this is my answer. All right. If I have a calculator, I push the buttons. Maybe. Being a little slow here. And it's about negative 0.2940. So there's 2. Way easier than ACT, isn't it? Of course, I've been picking the hard ACT questions. Here's a graphing problem. Graph y equals the negative natural log of x plus 3 minus 4. This one's going to have some shifts going on. It's going to go, look at that, plus 3 from x plus 3. I think left 3. The minus 4 literally means down 4. So left 3. Down 4. It's also negative. Normally you talk about the natural log of something. Talking about a graph that looks like that. Not this one. Not this one. This one's negative. Negative natural log of x is going to be a vertical reflection. So it's going to look like this. Now the vertical asymptote's already shown itself. It's right there. This is your vertical asymptote. It said x equals -3. It is the horizontal shift of the logarithm. Its range, I can tell you right now, is going to be from -3 to infinity. And its domain, sorry, its range, I did that backwards. Its domain is going to be from -3 to infinity. And its range is going to be like it is for every logarithm, -infinity to positive infinity. And now we're tasked with actually doing the graphing. It's only going to be able to work to the right of your asymptote. If there was a negative inside of x plus 3, it would be drawn left. But -3 is going to be an asymptote. Maybe plug in a -2, a -1, a 0, and a 1. None of them are going to give nice answers. They're not. And for you watching the video, you know, nobody's really going to ask you to graph these by hand. It's not a skill. At least not a skill for an Algebra 2 kid. ln x plus 3. Zoom, oops, I forgot something, -4. Zoom, 6. Now, your TI-84 does not graph properly. It does not do it. It doesn't happen. Oh, I forgot the negative symbol, didn't I? That's why it doesn't look right. Negative ln x plus 3 -4. And again, a TI-84 doesn't graph right. This is supposed to shoot straight up. Just an incompatibility with the thing. That's what it is. Anyways, the reason I did that was I can go to second table. And there's some points. Like there's -2, 4, and so forth. I'm going to be exceptionally lazy. Just going to take that. Going to copy it. Gives me my points. There we go. So -2 happened to be -4. -1 happens to be getting really close to -5. 0 is a little past -5. And kind of that's the gist of it. Oh, man. I put that in the wrong spot, didn't I? Bummer. I hope you caught that at home. 1, 2, 3. This is my shift. So it was downfall. Having a bad day here. Anyways, 2 was -4. -1 was -4.6. 2 is all the way at almost 6. And I'm having a hard time for some reason with curvature on this thing. It's supposed to come in from up high, hit these points, and just kind of almost flatline. It actually doesn't flatline. It goes down forever. And there's my upside down R. There she is. And I don't know what was wrong with me on that problem. I apologize. 9's a logarithm. Graph y equals log base 2 of x minus 5 plus 3. So from x minus 5, we have a right 5. And the plus 3 means up 3. Right 5. Up 3. and the logarithm is going to be in here. It is. The smallest thing you can actually plug into this thing is a 6. Now I'm actually going to do some math here. Log base 2 of 6 minus 5 plus 3 is log base 2 of 1 plus 3. This says power of 2 equal to 1. And the answer, that's 0. So 0 plus 3 is 3. You don't have to use technology for things if you understand things. It's just the way it is. 7 will generate a result. 7 minus 5 is 2. Log base 2 of 2 plus 3. This is 1 plus 3, which is 4. 9 will generate a result. 9 would be log base 2 of 4 plus 3, because 9 minus 5 is 4. 2 plus 3 is 5. And if the reason I'm doing this one by hand is you don't have a log base 2 button. No log base 2 button. I haven't shown you change of base yet. So I'm doing this. Anyways, what do we have on here? We have the 0.63 right there. We have the 0.74, which is right here. And we have the 0.95, which is right there. And I just draw my R. Those logarithms look like R's. Remember, it's logarithm. They look like R's. All right, number 11, using logs and not y1, y2, a town has a population of 4,600 and grows at a rate of 0.23%. Keyword. Every 6 months. So when I do my formula for exponential growth, because it is growing, I introduce a /6 every 6. All right. My principal is 4,600. 1 plus that's 0.23%, which is equal to 0.0023. 50 over 6. I put those two numbers together. And I have a model. After time, that's the population of the town. I want to know when I reach 6,400. So I'm going to plug that 6,400 into the left-hand side. It's an amount. Try this again. Actually, I wanted it to be a different color. What I'm going to do is I'm going to isolate the base. So I'm going to divide out 4,600. And 64 and 46 are even. That's 32 over 23. And now I'm going to convert to a log. So convert to log is base. Boy, this is going to be funny, isn't it? So I guess I'm going to have to show you something else, aren't I? I kind of figured this would show up. I'm going to have a logarithm whose base is this funky looking thing, whose argument is 32 over 23, and it equals the exponent of t over 6. Now, this is kind of a look ahead. A logarithm base b argument a can be written natural log of a over natural log of b. So I can take this and I can say, okay, this is the natural log of 32/23 over the natural log of 1.0023. This is called change of base. And that would equal t over 6. And you'll go to your calculator. Perhaps you'll go to your calculator. We had natural log of 32 over 23. Pressing enter, I get this number, whatever that is, I don't really care. And I divide it by the natural log of 1.0023. Interesting. Oh, 1.0023. I probably need to stop. I must be tired. Divided by natural log of 1.0023. And I get this funky decimal. 143.7484. 143.7484. Then forgot it. 143.7484 equals t over 6. And now what we're going to do is we're going to multiply by 6. Because we want to counteract that division of 6. I don't know why I keep thinking I can use that there. Whatever. And we get about 863. It's a life form we're going to round up. About, oh, sorry, that's in months. 862.5 months. And we're just going to keep it with that. So, equals 862.5 months. Now, you shouldn't talk like that. You shouldn't. Nobody has any idea what that is without doing math. And you shouldn't ask people to do math because they don't like doing math. Divided by 12, we get about 72 years. All right, about 72 years. So that's what I'm going to go with. It's about 72 years. Because it's not growing too much. It's growing very slowly. And I'm going to pause this until I can get back in here. All right, so here we have 13. The task here is to create a table for f of x equals 2 times 1/2 to the x. And then use your table to create a table for its inverse. This is actually a good way of graphing logarithms, believe it or not, is to graph its inverse first. So I'm going to make a small table, and I'm going to be kind of picky about the values I feed it. I'm going to feed it mostly negative values. What do I want to feed this thing? I'm going to start off with -3. No, I'm going to start off with -2. This would be, and I'm just not going to call it my table here. This would be 2 times 1/2 to the -2nd, which is 2 times 2 squared. It has to deal with what happens here, which is going to be 8. If I feed it a -1, I'd have 2 times 1/2 to the -1st, which is 2 times 2. Because I wish you guys understood exponents. This becomes 1 to the -1 over 2 to the -1, which becomes 2 over 1. That's what the exponents do to it. If I feed it a 0, even a monkey would figure that one out. It's 2. Then I'm just going to feed it a 1. I'm not going to go any farther past a 1 because then I introduce fractions, but 2 times 1/2 to the first is 1. Yes. And there's my table. All right, use your table from 1 to create a table for the inverse. The inverse is they swap x and y. So in this table, and we'll call this f to the negative first of x, because we actually haven't written it yet. But the x's become 8, 4, 2, 1. And the y's become negative 2, negative 1, 0, 1. And this inverse is going to be a logarithm, because this was an exponential. And they are inverses. Step 3 is to actually find the inverse. And the first step is to swap x and y. So this y becomes x. And this x becomes y. Part 2 is to resolve for y. And I'm going to have to divide out my 2 first. X over 2 equals 1/2 to the y. Here's a base. Here's an exponent. This must be the answer. So log base to 1/2, whose argument is x over 2, is my y. And of course that y becomes f to the negative first of x. And then I'm going to graph it. And I'm going to graph it based on my table. So when x is negative 2, the y value is 8. When x is negative 1, the y value is 4. When x is 0, the y value is 2. And then 1, 1. Here is the first function. It's going to flatline right there. This is y equals 2 times 1/2 to the x. The logarithm, which I'll do in a different color, do in purple, is right here. When x is 8, y is negative 2. When x is 4, y is negative 1. When x is 2, y is 0. When x is 1, y is 1. This isn't the best example for showing inverses, but it's going to flatline on the y-axis. Notice that this guy flatlined on x-axis. The inverse has to flatline on y, because they're going to do the opposite things. And the last thing you're supposed to do is you're supposed to graph y equals x. Y equals x passes through the origin, passes through 1, 1, passes through negative 1, negative 1. And the reason you're being tasked with graphing that is to help you see the line of symmetry. So you can see the symmetry, how it's the same thing on both sides. It's been hot dogged over. The purple one was f to the negative 1 of x. And there's your graph, 413. And I do think that that is all of the homework. I really do. It is. So that video is finally done. Took me a while.